Okay, this is lesson 106, reviewing the effects of scaling on volume. So this large cube right here is 3 times wider and longer and taller than the small red cube. So that means I could fit 1, 2, 3 across there. I could fit 1, 2, and 3 across there, and 1, 2, and 3 across there. So really I have 3 across, 3 wide, and 3 high. So meaning I should be able to fit 3 times 3 times 3 small red cubes in the blue cube, which would be 3 times 3 is 9, then times 3 would give us 27 cubes. So it turns out there's 27 times more volume in the blue cube than there is the red cube. So if we were looking at volume, you would say multiply by 27. But wait, I thought you said the dimensions were only 3 times wider. It's because we have 3 dimensions that are times 3 times 3 times 3. So there is a math law in that, and that has to do with the ratio of volume. We'll skip right down here to volume. The ratio of volume is going to be whatever your scale factor is. In our case, we did dimensions times 3. Okay. You take your scale factor and you cube it because there are 3 dimensions: length, width, and height. If you were talking area, just a flat object, if you doubled your flat object, twice as high and twice as wide, you would take your scale factor times 2 and you would square it because there's only a length and a width times 2 times 2. So you would square it. If you were just comparing the lengths, it'd be the same as the scale factor. So if we times it by 2, it's just twice as long. So let's try a couple practice examples. A cube is doubled in dimensions. How many times bigger is the larger cube than the smaller cube in volume? So it's a little cube right here. We're going to double it, meaning we take that same size right there and make it again itself, the same height and again on itself. And there it is, twice as long and twice as high and twice as deep because it's a cube. There's 3 dimensions. So again, we did dimensions times 2. If we use our law that says the ratio of volume would be the scale factor, or 2 cubed, which is 2 times 2 times 2, or 8. So there are 8 small cubes that can fit in here. And let's see it, if we can see it in a picture, if that would help us see the 8 cubes. There's 1, 2, 3, 4 on the front face, and 1, 2, 3, 4 on the back face. So sure enough, there are 8. So this is 8 times more volume, or 8 times, not in dimension, but in volume, 8 times bigger. How about something round? I think we can do the more advanced problem now. A cylinder is tripled in dimensions. How many times bigger is the larger cylinder than the smaller cylinder in volume? So I've got a small cylinder. I make it 1, 2, 3. So let's just kind of estimate about 3 times, I'm going to run out of room, 3 times wider, 3 times taller. So this is going to, again, apply to our law that says the ratio of volume, in other words, the larger one divided by the smaller one. How many times bigger is the larger one? The scale factor cubed. Well, our scale factor, it says it's tripled. So really we're timesing by 3 in dimensions. So it should be the scale factor cubed, or we've already done that problem. It was 3 times 3 times 3, or 27. So this is 27 times more volume. All right, let's do another cylinder. A cylinder is 25% bigger in dimensions than a smaller cylinder. How many times bigger in volume is it? Okay, now let's think about this. If it's 25% bigger, that means, let's draw a little cylinder. It's only slightly bigger. Well, what do you mean 25%? Let's take a distance of, for example, 4, okay, for the width. Well, 25% of 4 would be a quarter of 4, or 1. In other words, I need to make it a slight bit bigger by adding 1 to that. So it's going to be 5 across. So again, if this is 100%, this is going to be 125%. So 25% more dimension than this one. Again, if this was 4 high, it would be 5 high. Okay, so this one is 25% bigger. Well, what is the scale factor if we've added 25%? Well, we would be timesing by 1.25. Or, if it's easier to see, it's 125% of the original size. Move the decimal over twice. So your scale factor is 1.25. That's very important. You're going to need this on your practice set. So it says, by what percent has it increased in volume? Oh, okay. So let's look. Our scale factor was 1.25. Let's use our law right here that the ratio of volume is scale factor cubed. Okay. So if our scale factor is 1.25, we can times by 1.25. Let's do 1.25 cubed. And we're going to pull out the little calculator, 1.25 cubed. So on my calculator, I'm going to hit the y to the x and give it the cubed power. And that equals 1.953125. I won't need all those digits. So that is the new, the ratio of the volumes. So that would be my large volume divided by my small volume. So I guess one way to think of it would be this volume times this number equals this number. So it says, by what percent has it increased in volume? If I went from 100% and I multiplied it by 1.95-ish, and I would get 195% more volume. So how much percent has increased? It would be 195% minus 100%. It has increased 95% in volume. That's actually a lot. It's kind of interesting because you think of, if the dimension is only 4 and all I add is 1 centimeter and make it a 5 and 5, I've almost got twice as much volume. I've increased it 100%. It's kind of interesting. See, again, I almost have 2 times the volume. So, so the answer is it's increased 95%. All right, I think I've got one more example. It says, let's pull that down there. Okay, the large brick has 1.5 times the length, the width, and height of the small brick. What is the ratio of the volume of the larger brick to the smaller brick? Okay, ratio of volume. Again, we learned that the ratio of volume is equal to scale factor cubed. Well, the scale factor is how many times bigger the dimensions are. So it's 1.5. So really, this doesn't require a whole lot of math other than knowing how to use the formula, putting 1.5 in as the scale factor and cubing it. So let's use our calculator again. And we're going to clear that. 1.5, and we'll use the exponent button on my calculator, give it the third power, and that equals 3.375, and that's the ratio of volume. Meaning this brick should have 3.375 of these smaller bricks inside of it. So if I worked them sideways, maybe here's a brick, and here's a brick, and then there's a little bit more of a brick. In fact, 0.375 of another brick. 1, 2, 3.375 small bricks inside this brick. So that leads us to an important question. How would we use that information? Well, how heavy is this brick? It says it's 3 pounds. So shouldn't this brick be 3.375 times heavier? Yes. So if we take 3 pounds, pounds times 3.375, because it says 3.375 times more volume. So let's keep our calculator handy before it times out. It did. 3.375, we're going to multiply that by the pounds, 3. And then that says our large brick should be 10.125 pounds in weight. So you can picture the application there. Someone's maybe considering, hey, you know, I want to increase my product size. Is my machinery, can it handle the weight? If I have something that's 3 times bigger, how much heavier is my product going to be? Can my pallets hold that much weight? What's my shipping costs going to be with this new weight? So that's a good application for how volume changes when we change dimension. So, all right, you guys that's it for the lesson, and I hope you all have a good day today.